The next property of multiplication that we'll look at is the commutative property, and we saw this property with addition as well. As long as you have all addition problems, right? So as long as your only operation is addition, you can change the order of the things that you are adding. And so the same is true for multiplication. So I could say, for example, for any numbers A and B, I know that if I multiply A times B together, I will get something equivalent to what I would get if I multiply B times A. And I might think of it differently, right? A groups of B each or B groups of A each, but I would get the same answer. So my product would be the same either way. And so as long as it's all multiplication, you can do this. You can change the order of your factors in any multiplication problem and still get the same answer. Now, we talked about when we did addition, we said, is subtraction commutative? It really isn't unless you move the negatives with it, right? So unless you make the subtraction signs negatives and you move them with the number, you can't subtract in a different order and get the same thing. So like, for example, we talked about 3 minus 2 versus 2 minus 3, right? You'd get positive 1 from the first one, you'd get negative 1 from the second one. So you can see subtraction is not commutative. And this is also true if we talk about division, right? I would get a different answer from 3 divided by 2 versus 2 divided by 3, right? So we can change the order if it's addition or multiplication, but strictly speaking, subtraction and division are not commutative. And then speaking of that, if I go back to the closure property works for multiplication. Does it work for division? So think about, like, if I have two whole numbers, let's say 3 and 4, I know that if I multiply those, I'll get 12, which is a nice whole number, right? So it makes sense. I multiplied two whole numbers, I get a whole number. But if I change that multiplication to division, 3 divided by 4, now that's a fraction, right? And so when you divide whole numbers, you don't necessarily get a whole number. So closure also does not hold for division. All right, and then we're going to talk a little bit about area, because this actually is a good visual method for talking about the commutative property. So we know that the area of a region is the number of unit squares needed to cover the region without gaps or overlaps. So for example, if I had, let's say, a rectangle, and let's say that this is 2 feet by 6 feet, right? Technically, I could split that up, right, and show the 2 feet going this way and the 6 feet going this way, right? I did not draw this to scale, and I'm not drawing it very well, but you get the idea. And so I could actually just find the area by counting how many of these individual square units, and again, pretend I've drawn that perfectly. How many of those square units does it take to cover that region? So that is really useful, because when we talk about an array, which an array could just be, any objects arranged into rows and columns, but technically if you've got, like I just drew, like if you've got a bunch of squares, right, that's an array, right? You can see that those are arranged in rows and columns. And so what's nice is that this area, so this one, for example, this might be a 2 by 4, right? A 2 by 4 array. And so I could multiply 2 by 4 to find the number of square units there. The nice thing is, if I rotate this, and so if you've got this written on a sheet of paper right now, you can actually rotate your paper to do that. If I rotate this, the area didn't change, right? But if I rotate it, all of a sudden, now it looks different, right? But the area is the same. And actually, this would be 4 times 2, right? So this demonstrates the commutative property really well. So we'll just write like an example here. So I'll say, for example, I'll just use 3 and 4. An array with 3 rows and 4 objects in each row has the same number of objects as an array with 4 rows and 3 objects in each row. And again, essentially they're the same array, just rotating them is a good idea or a good way to see that, because it's really just the same array rotated 90 degrees in one direction. So at this point, we're going to pause here in this section of notes. So before you go on and do the next property in this section, I actually want you to go ahead and complete class activity 4E.